Alright, today we're going to go over some projectile motion. This video is meant to be purely more of an intro kind of for projectile motion. We're going to go over just a basic concept. Okay. There'll be future videos to go over more complex problems. None of these problems, though, are going to be when we consider air resistance. For these problems, we're going to assume that gravity is uniform and that there is no air resistance. So we're in vacuum-like conditions. This makes the concept a little bit easier. The whole idea behind projectile motion is that the object that we're going to look at, okay, it's going to have a few things. Number one, it's going to have parabolic motion. Okay. Number two is that it's only going to be under the influence of gravity. That means since gravity only acts in our symbolic y direction, if we were to make a little coordinate grid here, then gravity is only going to act in the up and down direction. That means when an object's flying through the air, the free body diagram for that object is only going to have gravity, the force of gravity going down. You'll notice there's no vectors acting in my x direction here. So what that implies is that my acceleration in the x direction is always going to be 0 for this problem, or at least for these problems. Okay, so we have a scenario here where I have independent movement. Okay, so I have x movement and I have y movement. Okay, so here's let's go over kind of just a very simple example. Now this video is not to be a supplement to what we learned or to be an exact replica of what we learned in class. Hopefully you took notes to that. But let's go over an example to kind of go over this idea. Let's say I've got a ball, okay, that I want to just drop off a cliff. All right. Now we're going to look at this in three different ways. Okay. First is we're just going to analyze it as the ball goes down. Okay. We're going to analyze it as if gravity didn't exist and I was just to throw it straight. And then we're going to analyze it and look at what it looks like in real life if I was to throw it off a cliff. Okay. Now, if I drop a ball from the top here, okay, then I only have motion in one direction. I've got motion in just the y direction, which is pretty standard. Okay, those are the types of problems that we were doing for the first part of the year. You may not look at it this way, but this is an initial position, and the ball is going to fall. All right, only under the influence of gravity. When we use our kinematic equations, we're going to use this equation quite often. Now you could change out y's for x's or vice versa. Okay, this equation we're going to adapt to a projectile. Right here, at least for this scenario, my y initial is 0 and my initial velocity in the y direction when I drop the ball is also 0. Okay, so my y final is dependent on just gravity and the amount of time that it's falling. Okay, gravity being my ay and the t here. All right. So when I drop this, if I put in say 1 second, okay, and for the sake of easy math, we're going to just say gravity is a standard 10 meters per second squared. Okay, and I plug in a value of 1 for 1 second. Square that. 1 squared is just 1 times 10 is 10 times 1/2, and I get a bombing 5 meters or so that this ball is dropped in 1 second. So we'll just say that's about right here. Okay, so this is 1 second. Okay, if I put in at 2 seconds, okay, this is 2 seconds from my initial drop. It's not 2 seconds after this, it's 2 seconds from my initial position. Okay, because all these are still 0 for the equation, right? So 2 squared is 4 times 10 is 40, divided by a half is 20. So this is 5, that means 20 is going to be somewhere around here. That's 2 seconds. Let's do one more. We got 1/2, okay, and I've got 10 meters per second squared. We'll do 3 seconds now, squared. Okay, so 3 times 2 is what? That's, well, sorry, 3 squared. So 3 times 3 is 9, times 10 is 90, times 1/2 is 45. Okay, so 45 meters, so obviously that's going to be somewhere way down here. So at 3 seconds. And you can't even see that. We're doing it way down there. All right, so you can tell that the distances here between the seconds is increasing. Okay, it's not something that how do I say this? It's not just equal increments. Okay, this is a square, it's an exponential. Okay, and so that's going to grow. Now let's look here. Let's just assume gravity didn't exist for a second. Okay, and we just throw the ball at some Vx, okay, velocity in the x direction. Now, since on my original free body diagram, if we scratch gravity, that doesn't change what's happening in the x direction. Nothing's changing there. So if after it leaves the hand, it's just going to go at a constant speed, and so it's just going to appear here. 1 second after another. Okay, so 1 second, 2 seconds, 3 seconds, and these are constant. Notice these right here, these intervals, they're equal to each other, okay? Because in this scenario, there's nothing to cause them to speed up or slow down in the x direction. My initial and final velocities in the x direction are the same. Now, we get the parabolic motion when we combine these two paths, because this is really what's happening when we throw, say, a ball off a cliff. We start off with an initial velocity in the x direction that's just going to end up being constant, because there's nothing acting on the ball to keep it from slowing down, or sorry, to cause it to slow down or to speed up. We have nothing to dictate that. And so what we do is we just line up so see how this lines up here? So the ball is going in both directions. And if we make, a curve there, and let's see if I can zoom this out a little bit. Okay, then we get that parabolic motion. And that's all that's really happening with projectile motion here, is that we have the ball undergoing a y change, and we have a ball or an object or some type of projectile undergoing an x change at the same time. But we compensate for both of those. Now, in future problems, and we're going to discuss this in later videos, but in future problems, we have scenarios, we have moments where we need to connect what happens in the y with what happens in the x. I want you to notice here that when the ball has reached this position, it has both gone all the way in the y and all the way in the x in the same amount of time. Notice, time in my equation here is non-directional. There's no x or y attached to that t. So t, time, is what links the two types of equations. Okay, and that's really important that we focus on that. If you need to jump between equations, like an x equation or a y equation, then we use time to be our liaison between them. Okay, so if you have any questions, I know this is kind of a foreign concept for a lot of us right now. Okay, if you have any questions, feel free to come in and ask. I'll be posting more videos. But this is just a simple example to show how an object is both falling and going in the x direction at the same time to get that parabolic motion of a projectile.